Welcome everyone to this breakout session where we will be talking about zero downtime data relocation with Vitess. My name is Deepthi Sigireddi. I'm a software engineer at PlanetScale, and I'm also a maintainer of Vitess. I have been working on Vitess for almost 2 years now, and I've been a maintainer for over a year.
And my name is Liz Van Dijk. I'm a solution architect at PlanetScale. I joined the company about 9 months ago, but given everything there is to know about Vitess and Kubernetes, I still feel like a newbie most of the time. My background is mainly in MySQL, since I previously worked at a company called Recona for about 7 years, and it's been really exciting to branch out into what I consider to be the logical evolution of MySQL in the Kubernetes-based world. So just to give you a little bit of background on PlanetScale, our co-founders created Vitess at YouTube about 10 years ago, and our mission is to make it the most trusted cloud-native relational database, period. We are headquartered in Mountain View, California, but I am personally based in Portugal, and Deepthi is based in Nevada. So it's not the first time we talk about data locality, but it does feel as though every time we get to share this topic, it becomes more relevant. We are recording this just weeks after the European Court of Justice repealed the US-EU Privacy Shield Agreement. Particularly global HR platforms have needed to pick up on this. You may have seen a blurb about this passing through your inbox, but in a nutshell, that agreement made it easier for personal data about EU citizens to be exported to the United States. And it's just the next in a long line of similar rulings that have been changing the legal landscape around personal data. More and more countries are putting measures in place that require personally identifiable information about their citizens to be kept within certain boundaries. And it can feel as though, for now, these laws are targeted at very specific hyperscale data companies. And while that's certainly true, this is a trend that's not reversing anytime soon. So after the ruckus of getting our companies in good shape for GDPR back in 2018, business leaders have been rightfully aiming to get ahead of whatever new requirements are coming and are considering what it's going to take to reshape those data stores. Now, building new applications with data locality in mind is daunting, but it's not impossible. Implementing it into existing applications that were never architected for that purpose is a whole different level of complexity, though. We want to show you today that Vitess can help you avoid needing to fully re-architect what you already have in place, and that it has the tools built in for allowing the transition of your existing data. And yes, that it's possible to do so with no downtime for the application itself. So let's get to the star in the story. I will go into some of the basic Vitess concepts to build some understanding around what goes into solving this issue. And Deepthi is going to demonstrate to you how to use those elements to achieve our goal. Though we have a lot going on in this diagram, the quickest way to explain what Vitess is as a middleware layer between your application and multiple clusters of MySQL servers. To your application, on the left of the dotted line, it presents itself as a single giant MySQL database. It speaks the MySQL protocol. You use standard MySQL connectors to communicate with it, and it's pretty straightforward. Of course, internally, there's a lot more complexity. Vitess is built to accommodate transparent horizontal sharding, and there's many components that contribute to that. Just in case the concept of horizontal sharding is not yet 100% clear, the basic principle behind it is that we take the data within a single given table and we spread it across multiple shard clusters. So, for example, if you have a table that contains 4 billion rows, we can spread those evenly across 4 shards containing 1 billion rows each. The schema for each of these shards is identical. And to your application, the data still looks as though it's coming from one and the same table. In this talk, we're going to be focusing primarily on what's in the query path, which is represented by the white line sphere. Outside of that live VTCTLD and our topology servers. Those help us manage the infrastructure, but they're kind of less relevant to our talk. I do want to draw some special attention to VT-Gate. By itself, VT-Gate is your application's entry point to the cluster. It's a very light, stateless proxy, which contains an SQL parser, and it keeps itself informed as to the state of the cluster, so it knows exactly how to break down your requests at any given time. It's going to transparently select the correct shard for you to select from, and it supports and respects a very large variety of native SQL terms, like joins and transactions. It's also got a couple of built-in optimizations, like connection pooling, to help boost performance. Now, zooming in on the actual cluster and the shards themselves, there's a couple of logical and physical components that help establish them. The unified database, as represented by VT-Gate, is defined in Vitess as a key space. The key space is what established the logical layout of our data across one or multiple shards, and it's defined by a combination of our normal MySQL schema file, as well as something we call the v-schema, which describes the sharding-related metadata in JSON format. The v-schema is important for us to understand because it's where we define our application-specific sharding needs, as well as where we collect configurations for any Vitess-specific features we'd like to use on a table-by-table basis. So effectively, the v-schema is where you build the sharding logic for your application, allowing it to remain abstracted from your code. Now, at its most basic definition, sharding of tables happens by assigning every row a specific key space ID. This uses a computed column, the so-called sharding key. And it will associate each row to a physical address in a very specific shard. And that means that each shard is defined as the owner of a specific range of key space IDs. The way that's established is defined in the v-schema, and consistently, it's enforced by VT-Gate. Deepthi's going to go into what that looks like in the demo shortly. The shards themselves, as you've seen from these graphics, are not necessarily made up of a single MySQL instance either. They are effectively mini clusters of MySQL instances, and all of them make use of standard MySQL replication internally to make sure that there's multiple copies of your data present and to allow you to scale reads as needed. So zooming in on what makes a MySQL instance a part of Vitess, we're looking at a small sidecar process called the Vitess tablet, or VT tablet, which acts as an agent of cluster awareness. It connects to any existing version of a running MySQL server. That can be any flavor, running anywhere. We also include cloud instances to that, like RDS or Aurora. And effectively what it does is it adopts that instance into the greater Vitess cluster and makes sure that it's got a correct copy of the data and is configured to execute its given role. Now, somewhere between these two layers, or rather kind of transparently woven into the logical concept of a key space and the physical implementation of the Vitess tablets, is what we call a cell. And the cell is analogous to what we recognize as failure domains or zones in Kubernetes. They allow us to spread a given key space across multiple geographical locations. The actual definition of a cell doesn't need to imply geographical spread, and we could define them as different racks in the same data center. But for the purposes of our demo, we're opting to let the cells be defined as the geographical boundaries for the data, as set forth by the data locality requirements. Now, to accomplish a truly transparent to your application distribution of data, a normal horizontal sharding strategy is not going to suffice, a strategy that evenly spreads your data across the shards. We're going to need to build in some additional logic that's specific to the rule sets that we're trying to comply with. And we want to keep in mind that this is a moving target because, as we've seen in the past few years, those rules can be very dynamic and they change rather quickly. So let's take a closer look at a specific part of the V schema that we call the Vindex. Vindexes provide the bridge between the database's column values and a specific shard's key space ID, which is the internal physical address that gets attached to each row. And it helps establish the correct shard for that row. We'll use the Vindexes to define which columns to shard on, and specifically, which of the established sharding functions to use. Now, just like with normal indexes, sharded tables need to have at least a primary Vindex, but you could also create secondary Vindexes. Now, unlike a normal index in MySQL, Vindexes are not actually stored anywhere on disk because they are computed. And they use the selected sharding function, of which there's multiple included by default in Vitess, as well as the value for the row in the specified sharding column. To give you a quick idea, here are some of the included sharding functions already present within Vitess, and they cover a variety of common use cases. Most often, we're going to see the Vindex defined as a simple hash for an existing primary key, or we could use Unicode loose MD5 when we're using text-based columns. But as you can see from the numeric static map, sharding functions can also take a predefined list external to the database as a guide. And specific to this demo, sharding functions can be built to any specification you need. Now, with all of those concepts and ingredients, let's get back to solving the problem of data locality at hand. What we need to get started is a clearly defined list of jurisdictions, so a list of the cells across which we'll establish our key space. Deepthi is going to show you how to establish a sharding function that allows us to confine location-specific rows to the correct shards, and she'll show you how to execute that in place, beginning from an existing unsharded data set.
In this demo, we have 3 regions and 8 countries, and the regions are Americas, Europe, and Asia, and the countries are US, Canada, France, Germany, etc. So we are using region here in the sense of the English word region, not specifically cloud providers region. But what we have done is mapped each of these physical regions to cloud provider zones. The sharding scheme we will be using for the demo is to use a region JSON Vindex. This is a Vindex that is a multi-column Vindex. Until late last year, Vitess only had single column indexes, but as we realized that we should be working towards data locality requirements, we added a multi-column Vindex. And what this specific region JSON Vindex implementation does is that it maps an ID location tuple to a key space ID, and it looks up a byte value for the location using the map. And it uses that byte value as the leading byte of the key space ID, and that's how we achieve the sharding. There are 3 Vitess cells in each of these regions, and there's only one key space called main with 3 shards. Each shard is resident in 3 different cells. This is because on the PlanetScale production environment, whenever you deploy 3 instances, they are spread out to 3 different cells for disaster recovery purposes. The key space is split into 3 key ranges. -40 corresponds to US, and the byte values we are using for US and Canada are 1 and 2. 40 to 80 corresponds to Europe, and for France and Germany, we are using the hex values 40 and 41, which correspond to 64 and 65. 80- is Asia, and the byte values we are using are, they correspond to 128, 129, and whatever C0, C1 is for India and Indonesia. Now let's get to the demo. So here is our demo cluster, and in this we have a key space called main, which we have already deployed. And in this key space, we have two clusters. We actually have an unsharded cluster, which we are representing with a dash to denote that it covers the whole key space. And we have a sharded cluster, which has three shards, dash 40, 40-80, and 80 dash. We can look at the instances that we have in this cluster and filter them by shard. So we have three unsharded instances, one in Asia, one in Europe, one in the US. And in each shard, we have three instances, but they are all located in the same region. So for dash 40, we have US, 40 to 80, all of the instances are in Europe, and 80 dash, all of the instances are in Asia. Now that we have looked at the cluster configuration, let's also take a look at the schema and vSchema. The schema is very simple. We just have one table called customer. It has an ID field, which is a unique identifier, and a full name and national ID, which are the personally identifiable information. And there's a country field, which is our location. So that is the field that we are going to use during the resharding to denote which part of the world the data should flow to. Let's now take a look at the vSchema that we have created. So this is a resharding. So we have created a vSchema that says sharding is true, and there is one Windex, which is of type region JSON, and we are calling it region VDX. And we are going to give it a country to byte map file, which contains the JSON. And this Windex uses 1 byte to represent the region. And on our customer table, we create this as a Windex, and we will apply this region VDX Windex to the ID and country columns. Now that we've looked at the schema, let's take a look at the data. So we've already pre-populated the database with some data, and after we do the resharding, we expect that this data will show up in the new shards. The next step is to actually go through the resharding. Before we do that, I want us to look at the traffic on these tablets. So we have our instances. Let's look at dash, our unsharded key space. And you can see that there was this spike in QPS that corresponded to when we looked at the data. If we look at one of the other shards, then we will see that there is actually no traffic on the child shards. They don't have any data yet. So now let's run the resharding command. What this will do is, first it will copy the schema, the table definition from the parent shard to the three shards that we are trying to get to. And after that, it'll actually copy all of the data from the parent shard to the new shards. So if we go back and look at one of the tablets, dash 40, we will see that there was some QPS. vReplication actually wrote some data into those tables. Okay, now that the resharding has copied the data over, we want to actually verify the data. But before we do that, we will switch reads so that we can read from the new instances. So let's do that. So the next command we are going to run is the switch reads command, which will divert all replica traffic to the new shards. Once that's complete, we can actually now say, okay, this is all of our data, 14 rows, but now let's actually switch shards, but select from a replica. And we see that in this shard, -40, there are only 4 rows. Now let's try the next shard, 40 to 80. And this one also has 4 rows, and all of this data belongs to Europe. The third shard, -80, should have all of the data that belongs to Asia. Oh, that was the wrong shard specification. So we see that the data has all been copied over, and we can access this data by routing our queries to a replica. The next step is to switch writes. So let's do that. Now, before we switch writes, let us start a client so that we can see what happens when you try to switch writes from an unsharded cluster to a sharded one. So I'm going to start this client, which will just write some rows into the main key space. And once that starts, we will switch writes. So to start with, this workflow is going to compute all of the steps it needs to perform. And once it knows what it needs to do, it'll go ahead and do it. Okay, so switch writes has succeeded. I'm going to let this customer writer run for a little longer so that we can show you the data and then stop it. Let's go back and look at the errors that we got while switch writes was happening. So we have 1, 2, 3, 4, 5, 6, about 8 errors. This client program inserts about 1 row every half a second. So we have 8 errors, so about 4 seconds of time during which writes to the cluster were actually being rejected. But still, we are saying that this is still zero downtime, because in a distributed system, the application should be able to tolerate transient failure. And this is a transient failure because we got a few errors and then we were able to go ahead and insert a whole bunch of data afterwards. And the errors only lasted a few seconds. So as long as applications are designed to be tolerant to transient errors, the application downtime will be 0. The users will actually not see any downtime from the application. Before we wrap up the demo, I do want to show you that all of this data that we inserted actually got into the database. So now if we try to select everything from customer, we have a whole bunch more data. And we can do what we did earlier again, where we select from one shard at a time. So let's start with the -40 shard. And this time, let's do a count. And there are 23 rows. Let's look at 40 to 80. We have 16 rows. And let's look at 80 dash. We have 22 rows. Now, let's look at the main key space. And that number should add up. 23 plus 16 plus 22 is 61. So that's all we have for the demo. Now let's go back to the slides. Let's recap what we did in this demo. We have a database where a geographic location corresponds to a data column in the database. This allows us to insert data in the correct shard and to select from the table. However, you cannot currently use a multi-column index to delete data in Vitess. What is needed for that to work is to create a single column index, and it's recommended that that should be created on the primary key column. There is a user guide on the Vitess website that describes how that can be done. The other thing I would like to mention is that storing location as a data column is not the only way to do location-based sharding. Perhaps there is already a column that includes encoded location information along with the primary key. If such a thing exists, then you can write a custom index that decodes the location information from the data column and achieves the sharding. We have a number of talks at the conference. There were 2 yesterday, and if you missed them, you might want to catch up with the recordings. And there are 2 more talks coming up. One is deep dive into Vitess, and the other one is multi-cloud Vitess talk. And these are happening in about an hour or so. That's all we had. Thank you very much.